Hello, this is Sergio Cicero from University of Cantabria, and I'm going to present a work entitled Assessment of Notched PVC tubular beams using the theory of critical distances and finite element analysis. A work that has been completed in collaboration with my colleagues Marco Sanchez and Borja Arroyo. The presentation is divided in these four sections: an introduction, explaining the reasons for this analysis, the materials and methods used in the research, results and discussion, and finally, the conclusions. PVC is a polymer that it is actually being used in load-bearing applications, and as any other engineering materials, there may be defects on the corresponding structural components that limit the load-bearing capacity. So it is necessary to provide methodologies which are capable to predict fracture loads on structural components made of this material and containing defects, not only cracks, but also other types of defects, such as, for example, notches. When dealing with this kind of non-planar defects, when dealing with notches, the theory of critical distances is probably one of the most well-known methodologies. And this theory of critical distances methodology has had a wide development in the last years thanks to the use of finite element analysis. However, this theory, which has been widely validated for different failure modes and for different types of materials, this validation has been generally performed on fracture mechanics notched samples, for example, CT specimens, CMB specimens containing notches. But there are very few amount of works, if any, validating the theory on, let's say, demonstrators, that is, real scale components. And this is the purpose of this work, to demonstrate the capacity of the theory of critical distances in combination with finite element analysis to provide fracture loads on real components. Just to refresh the concept of notch, what do we understand as a notch? We are used to work in fracture mechanics community with cracks, that is, defects, flat defects on which the radius on the tip tends to 0. But when we have any other type of defect with a non-zero radius here, that's what we call notch. It may be a U notch, a V notch, etc. Well, as I said, we are going to use the theory of critical distances that at the end is using linear elastic fracture mechanics tools together with an additional material length scale parameter, which is the proper critical distance that follows this expression here, on which this term is called the inherent strength, but it is actually the ultimate tensile strength in materials with linear elastic fracture mechanisms in both micro and macro scales. If it is not the case, sigma 0 and L needs to be calibrated, and that's what happened with the PVC. Once we have L, the theory of critical distances, and particularly one of its methodologies, the point method, establishes that failure takes place when the applied stress at a distance of half of the critical distance equates the inherent strength. So here you have the corresponding picture. This is the stress field corresponding to the external critical load, because at the given distance, half of the critical distance, we have the inherent strength. All this being a linear elastic simulation. So for this analysis, we had 4 PVC tubes. One of them was used to characterize the material in terms of tensile properties and fracture properties. So from one of these tubes, different specimens were machined to better know the properties of the material being analyzed. And the other 3 tubes were the proper demonstrators. Here you have the characteristics of the 3 demonstrators and schematic showing where we introduce the defect. Here is a U-shaped notch with 2A being the defect length, and here we have the defect radius, and we applied a load on the extreme of the cantilever beam. Here it is encastrated in a concrete block. We combine different geometries, as you may see here, not only for the proper tubes, but also for the geometry of the notches. So we completed a set of fracture tests on notched fracture mechanics specimens, 3 point bending specimens containing notches, to calibrate L. So we obtained their critical loads, and then we represented the finite element analysis results in terms of the stress fields at the notch tips. And with that, we obtain L and the inherent strength. When we know these parameters, we simulated the tubes as well, and we introduce the external load till at the notch tip we reached the critical conditions. The simulation in the tubes was made for a unit load, and then finally we obtained the load bearing capacity estimation by scaling this simulation. Here you have the main experimental results obtained in the tensile and fracture specimens. These are the basic tensile properties with the corresponding standard deviations, and these are the results obtained on the notched fracture specimens, where you can see a clear notch effect, because for crack-like defects we have less than a half of the apparent fracture toughness observed in 2 millimeter notch radius. Here you have 2 graphs. The one on the top corresponds to the fracture specimens with a clear notch effect. This is the cracked CNB specimen, and these are the notched ones. As long as you introduce higher and higher notch radii, you obtain a much larger displacements on the test, so the behavior is more ductile, more non-linear. And the figure on the bottom corresponds to the load displacement results of the tubes, of the demonstrators, where you can see that 2 of the demonstrators had a very similar result, and there was a third one with a quite different behavior. Again, these are the stress fields at, failure of the fracture calibration specimens. And by obtaining the average values of these crossing points, we obtain half um, of the critical distance and the inherent strength. That should be half of the length should be around 0.07 millimeters, and the inherent strength should be a bit lower than 200 megapascals. And these results on the bottom are the stress fields on the notch tip of the demonstrators, which are subsequently scaled to derive the load bearing capacity estimations. And here you have the results. From the fracture calibration tests, we obtained these parameters for the PVC, and by using them on the demonstrators, we obtain these estimations of the load bearing capacity that can be directly compared with the experimental values. If we represent the results in a graph and we assume satisfactory results between the mass plus minus 20% of difference if compared with experimental results, the results are rather good because all of them are between these margins. So, with all this, the main conclusions are the following. We have combined the theory of critical distances with finite element analysis for estimating the critical loads on tubular beams containing U-notches, actually through thickness circumferential notches. The predictions fit quite well the experimental results, all of them being within the acceptance margins and with an average overestimation of 5% approximately. And another thing which is important to mention is that the overestimation is greater in those tubes experiencing more nonlinear behavior. So the more nonlinear the behavior is, the lower the final accuracy, which is normal if we take into account that the theory of critical distances, as it has been used here, is based on linear elastic assumptions. So that's all. If you have any questions, it will be a pleasure to answer them. Bye-bye.